Okay, so now that we know how to express the solubility of um, sparingly soluble salts using equilibrium expressions, we can now use that information to predict whether precipitates or solids will form in a reaction. And there are a couple conditions that can exist. We can have a solution that is unsaturated, meaning more solid can dissolve or is able to be dissolved. We have a saturated solution that contains the maximum of solute. And then we have a supersaturated solution that contains more than the maximum of solute. Okay, and those are inherently unstable solutions. So how can we predict whether a precipitate, whether a solid will form in a solution? Well, what we're going to use here is the reaction quotient that we saw way back, which we abbreviated as Q. And the reaction quotient, remember, is the similar expression to the K expression. However, it is not at equilibrium, it is at any point, right? So the Q is the equilibrium expression at any point along the reaction pathway. So we can compare the Q value, the reaction quotient, to the KSP. And if Q is less than KSP, no precipitate will form. That means at that point in time, we haven't reached the saturation point yet. If Q is equal to KSP, no precipitate will form either. But if Q is greater than KSP, then the precipitate, a solid, will actually form in that situation. So let's take a look at an example. We'll do just one of these for right now. So we're going to take a look, first of all, at predicting whether a precipitate will form when each of the following is added to 650 mils of a 0.080 molar potassium sulfate solution, right? So we have K2SO4. Solution concentration here is 0.080 molar. Okay, and we have 650 milliliters of that solution. So let's look at the first one. We're adding to that solution 250 mils of 0.004 molar barium chloride solution to this. Okay, so let's take a look. We have 250 mils of 0.0040 molar BA Cl2. So for each of these combinations, we want to identify the compound that could precipitate. So ID, the combination that could precipitate out, meaning that could form a solid. Right? Precipitate is just a solid. And then we're going to look up the KSP value from our tables and then determine the concentration of each of the compounds constituents ions. Okay, so determine the concentration of the ions in the compound, and then use them to determine Q, the reaction quotient, and compare it to the KSP. Okay, so that's the first thing that we're going to take a look at. So in this first combination here, we have K2SO4 reacting with BaCl2, right? So the combinations here that could form would be barium sulfate. So we're swapping the ions, and that's a double replacement reaction. So we can get barium sulfate would be one combination, and then the other combination would be potassium chloride, KCl. right? So but group 1 metal ion compounds are soluble. So the only other thing that could form precipitate would be this one, right? So potassium salts are always soluble. You can look at your solubility table to determine this. So this here would be our candidate, right? We're using stuff we learned way back in Gen Chem 1, right? We have 2 ionic compounds. We can predict double replacement. We swap the cations to make new combinations. So the barium sulfate, the KSP for this, if we look it up in our tables, is 1.1 times 10 to the negative 10, right? So yes, that's a fairly small value for KSP. We can go ahead and use that one to determine. So let's take a look. Barium sulfate, BaSO4, right, is made up of the barium ion, Ba2 plus, and then we also have the sulfate ion, SO4 2 minus. So what are the concentrations of these? Well, the concentration of the barium ion, well, where does the barium come from? It comes from the barium chloride. Okay, that's this thing here. And we have 250 mils of the barium chloride. So let's do 250 mils is the same as 2.250 liters of the BaCl2. Okay, we have the concentration as 0.0040 molar, 0.0040 moles of barium chloride per liter. So the liters go away. And then I just want the barium ion. So for every 1 mole of the BaCl2, I have 1 mole of the barium ion, right? So the moles of barium chloride go away. So now I have moles of barium ion per liter. I stick that in my calculator. And I end up with, let's see. So 0.25 times 0.004 would give whatever, let's just say X moles of Ba2 plus. Well, that's the moles of Ba2 plus. What's the total volume though? We added the 250 mils to 650 mils, right? So the total volume here is 650 plus 250, right? That's 6 plus 2 is 8, so that gives 900 milliliters, right? So that's what we need to divide our moles of barium by. So 900 mils is the same as 0.900 liters, and then that's going to give us 0.0011 molar for the concentration of the barium, right? We need to consider what the total volume is. The sulfate, on the other hand, the SO4 2 minus, right? That's going to come from the potassium sulfate, the K2SO4. Okay, how much do we have? We have 650 mils. So that's 0.650 liters of the K2SO4. The concentration was 0.0080 moles per liter. Okay, and then the ratio here is we have 1 sulfate and 1 SO4 2 minus for every 1 of the potassium sulfate. Okay, so there we end up with, let's say Y, this is moles. Say Y moles of the SO4 2 minus ions. We're going to divide it by the total volume, which is the same, 0.900 liters as above. That's going to give 0.0058 molar for the sulfate ion. Okay, so then we need to stick that into our equation, our calculation. Okay, so we get our Q, our reaction quotient then would be equal to the barium times the sulfate. So that's, what do we get? 0.0011 times 0.0058. And that gives 6.4 times 10 to the minus 6. So that's our Q. We compare that to KSP. The KSP there was 1.1 times 10 to the negative 10. Okay, so so Q is greater than the KSP, so we can predict, you can say, yes, a precipitate will form. Right, and the way that I can quickly tell, look at the exponent, right? It's a negative exponent, but it's a smaller value. That means it's a bigger number compared to the KSP. So when you do these calculations, right, make sure that you pay attention to the stoichiometry of when these ionic compounds dissolve. Make sure that you even before that, make sure that you predict the products properly as well. That way, we make sure that we determine the correct KSP value, looking them up in the tables.